Hello students, welcome to Tuteetute. In our last session, we have seen previous year questions from GENCO 2015 Telangana state. Okay, so similarly power systems questions we will see in this session. So I'm not adding the power plant engineering questions or generation concepts in this video. So I will make the power plant engineering as a separate video because other students also can watch that classes. Okay, so anyway, let's see the power system questions. So the main criterion for selection of size of radial distribution system. Okay, so for the distribution system, whether that is a radial distribution system or Ringman distribution system, so what is the problem with this distribution systems means there are more voltage drops. Okay, so that's why, so even the radial distribution system is having more voltage drop compared to Ringman distribution systems. Okay, so that means comparison, if you do the comparison between radial and Ringman distribution system is more reliable. Okay, so that's what some more advantages also there for the Ringman distribution system. Anyway, it's a distribution system. So what is the main problem with the distribution system is the voltage drop. Okay, so this is the only answer here. Okay, so the next question, the insulation resistance of a cable of length 10 km is 1 mega ohm for a length of 100 kilometers. Okay, so of the same cable, the insulation resistance will be, okay, so insulation resistance or insulation they are asking, so that will be equals to rho divided by, okay, so rho divided by 2 pi l. Okay, so rho by 2 pi l into ln r by r. Okay, so this is the formula. R is the radius of the sheath outside. Okay, so and small r will be the radius of the core material. Okay, so that means if this is the core, on the core there will be insulating material. This is all insulating material. So this insulating material only, so they are asking. Okay, so resistance. Okay, so this will be how much of length they are asking about 100 kilometer. Previously for 10 kilometers, this is the one. Whenever 100 kilometers, what will happen? Okay, so this is the formula. So no need to do all this. Okay, so rho insulation equals to R insulation. Okay, so our insulation resistance equals to, so we can directly give as inversely proportional to L. Okay, so this is only we need. Okay, so remaining all we don't need. So L inversely proportional here for the insulation resistance. So here 1 mega ohm for the 10 kilometers. Okay, so we can do directly. Okay, so R1 divided by R2 equals to L2 divided by L1. Okay, so R1 value is 1 mega ohm and R2 value we have to calculate, and L1 value is L2 value is 100 kilometer and L1 value is 10 kilometer. Okay, so 100 divided by, so 10 is nothing but 10 you will get. R2 value equals to 1 mega ohm divided by 10 you will be getting. Okay, so that means 1 mega ohm divided by 10 means 0.1 mega ohm. Okay, so just check the units and give the answer. Okay, so this is the answer for this. Okay, so next, for a 500 Hz frequency excitation, a 50 kilometer long power line will be modeled as. Okay, so see these questions in GENCO 2015 they have given as simple questions only, but more conceptual based questions they have mentioned. Okay, so may not expect similar kind of questions in the upcoming examination. Okay, so that's why, so you may not expect the similar kind. Okay, but conceptually we should be clarity. Okay, so on these concepts. Okay, so anyway I will give you, so for 500 Hz frequency excitation, a 50 kilometer long power line will be modeled as. So that's what they have given. So we need to make it as a short line, medium line or long line. Okay, so that's what they are asking. So let's see, generally if length of transmission line is less than 80 kilometer, so then that is a short line. Okay, so wait, okay, some may be thinking, so this is only for something, right? I will tell you all these. Okay, so when length of the line, okay, so in kilometers, it is between 160 kilometers to 80 kilometers, then we have to model this one as a medium line. Okay, so medium line. So if length of this transmission line, any transmission line is greater than 160 kilometers, so then we need to consider as long line. This is what generally we used to learn. Okay, so but this is valid for certain conditions. Okay, so whenever frequency equals to 50 Hz. Okay, so for that frequency, so there will be wavelength. Okay, so what is the wavelength? So wavelength lambda is equals to the velocity of the wave divided by the frequency. Okay, so this is the formula for this wavelength. Okay, so for this wavelength and for this frequency based on the wavelength, so this has been given. Okay, so this is the, so generally for the 50 hertz, now what they have mentioned, frequency is not 50 hertz here, frequency is 500 hertz. Whenever frequency increased from 50 hertz to 500 hertz, you see one thing, okay, lambda value will decrease, wavelength decreases. That means this much length may not be considering. Okay, so for any very short line also, okay, so we need to consider that as the long line. Okay, so that means for the 50 kilometer also we need to consider this one as the long transmission line, like that. Okay, so that's what the analysis. Okay, whenever frequency increases, so 10 times it has increased, right? Okay, so that means automatically, so any line which is having 50 kilometer or above also we need to consider. Okay, so if you need any more clarity about this one, okay, so you need to observe the textbook. Okay, so some more concepts we need to understand from this one, from the wavelength. Okay, so from the wavelength concept point of view. Okay, so anyhow, if you need any more explanation for this one, you ask me. Okay, so the next question, series capacitive compensation in EHV transmission line is used to. Okay, series capacitors they have given. Okay, that means in any transmission line, okay, so let's consider this is EHV. Okay, so EHV line, it is one capacitor, series capacitor we have mentioned previously. This line will be having some reactance, that will be X line, and this is XC. Okay, so that means capacitive reactance it is. Okay, so generally we will be considering as minus J it is. Okay, so this is plus J because it is line inductive reactance. Okay, so totally they have mentioned, so a series capacitive compensation they have did like this. That means a capacitor bank they have kept in the transmission line. Okay, so whatever line it is, no problem. Okay, so what will happen? Reduce the line loading. Okay, so let's see. Later, improve the stability of the system, reduce the voltage profile, improve the protection of the line. Okay, so see what is happening here. If you consider one of the capacitor in between this line, okay, so that means net reactance will be, it will become like previously it is X line only. Previously, okay, whenever capacitor bank is not present, X line only. Now whenever you have connect this capacitor bank here, then it will become as minus JXC. That means net reactance decreases. Whenever net reactance decreases, see what is happening. Generally electrical power output, okay, so electrical power output how we need to give, that means the active power receiving. Okay, so the active power receiving at this end. Okay, so that will be PE equals to, or electrical power equals to P max sine delta, otherwise we can consider as mod. Okay, so let's consider like this, P max sine delta. Okay, so this is the one. What is this P max? P max is nothing but our steady state stability limit. Okay, so this is nothing but the maximum power that can be transferred. Okay, this is the maximum limit we will be having. Okay, so let's consider what is this P max means. Generally E, that means sending end side voltage E and receiving end side voltage V at an angle of 0, and this is nothing but E at an angle of delta. Okay, so EV by X net into sine delta. So this is the one we need to consider. Okay, so this is the this is only P max. Okay, so this is only P max, so sine delta will not be there. So if it is electrical power output, then sine delta also we need to use. Okay, now X net decreased. Now X net decreased, that means P max will increase. Okay, so P max will increase whenever you connect series capacitive bank. Steady state stability limit or maximum power that can be transferred, okay, so that will be increased, otherwise stability limit improved. Okay, so like that we need to consider. Okay, improve the stability of the power system. Okay, so remaining all things are for the different elements, those are possible. Okay, so this is also one of the compensation, this is also one of the compensation, this is also one of the compensation, but not with the series capacitor. Okay, series capacitor mainly focuses on this steady state stability limit. Okay, so that means see previously how much power we are transferring, now also same power only we will transfer from one side to another side, but limit has been increased. That means we will get more safe operation of the synchronous generator or synchronous motors in the system. Okay, so that's what the answer for that question. Okay, so answer is, so what is the answer here? Improve the stability of the system. Okay, so that's what we can consider. Okay, so next one, the corona loss on a particular system at 50 Hz is 1 kilowatt per kilometer. per phase. Okay, the corona loss at 60 hertz would be, okay, so they are asking for 50 hertz they have mentioned. Okay, for 50 hertz they have mentioned the corona loss as one electrical corona loss. Okay, so 1 kilowatt per kilometer. Okay, so per phase. Okay, so this is what they have mentioned. Now frequency, if the frequency is not 50, 60 hertz, now they are asking about how much is the loss. Okay, so what is this relation? The corona loss directly proportional to f plus 25. Okay, so some may think, okay, f plus directly proportional to frequency. No, okay, f plus 25, this is the value. Okay, so otherwise the complete formula, okay, so I have just given here. So this is the corona loss formula. Okay, so 214 into 10 power minus 5 into f plus 25 divided by delta r by d whole power 1 by 2. Okay, so root of that is, okay, so v naught minus vc whole square kilowatt per kilometer. Okay, so consider the units also. Okay, so that's why this came. Okay, so if you unit changes, then it will be changed a little bit. So and if you want to just check these things. Okay, so if you remember this one, no problem. So it means f plus 25, it is proportional, loss is directly proportional to f plus 25. So based on this, okay, so power 1 in first case, in second case equals to f1 plus 25 divided by f2 plus 25 you will be getting. So that means in first case 1 kilowatt and second case we don't know, we need to calculate this one only. f1 plus 25, f1 is nothing but 50 hertz they have mentioned. So 50 plus 25 is 75 and this you will get as 85, 60 plus 25. Okay, so then what is P2 generally? 85 divided by 75, so it will be getting more than 1 only. Okay, so answer generally it has to be greater than 1. Okay, so greater than 1 point something you will be getting, but that option is not present here. Okay, so that means they might have given this question as wrong. Okay, so if they want like this, okay, so like here 60 hertz is there and here 50 hertz is there, then so the answer you will be getting the P2 equals to 75 divided by 85. Okay, so then you will be getting 8.88. Okay, so kilowatt per kilometer per phase. This answer you will be getting. Okay, so anyhow procedure we know how to solve, but this question they have given as wrong only. Okay, so next one, the severity of line to ground and 3-phase faults at the terminals of, okay, unloaded synchronous generator is to be the same. Okay, if the terminal voltage is 1.0 per unit and Z1 and Z2 equals to J 0.1 per unit, Z0 equals to J 0.05 per unit for the alternator, then the required inductive reactance of neutral grounding is, okay. So looks like big question only, but it will take only 1 minute to solve if you know the formula. Okay, so two types of faults they have mentioned. Okay, the severity of line to ground and 3-phase faults at the terminals of unloaded synchronous generator. Okay, as usual when we study the subject, so we will consider like this only. Okay, synchronous generator which is unloaded, otherwise no load operating synchronous generator we will consider. Okay, and they have mentioned in both the cases severity is same. Understanding? That means fault current, so with what is this fault? Line to ground fault. Okay, so LG fault is equals to fault current in 3-phase fault they have mentioned. That means either triple L fault or triple LG fault, anything you can consider. Okay, so like this they have given. So if you make this calculation, okay, so for this one formula is so 3 into so E per unit. Okay, so E per unit means already they have given as 1 only, no need to consider that. Okay, so 3 divided by x1 per unit plus x2 per unit plus x0 per unit plus 3 times of neutral reactance. Okay, so that means in the generator, okay, so in the generator there is certain neutral reactance is there. Okay, so we will represent as a 3xn. Why means there is certain calculation. Okay, in different question I will be explaining this why we are considering this 3xn. Otherwise if you have understood the classes already you will know this. Okay, so we need to represent the circuit point of view, that's why we have given as a 3xn here. Okay, so anyway in different question we will understand that also. Okay, so is equals to, so they have mentioned the fault current in this case is 1 divided by x1. Okay, so this is the fault current formula in per unit for the LG fault. This is the fault current formula for the triple L fault in per unit. Okay, so anyway you have to substitute these all values. Okay, x1 value or z1 value is 0.1 per unit. This is also 0.1, so this is 0.05 per unit. So totally will be getting so it will be 0.25. okay, so I'm not giving as a j. Okay, no need of that now, later we can give. Okay, so plus 3xn is equals to, so 1 divided by 0.1 means you will be getting 10. 1 divided by 0.1 is 10. Okay, so total it is, so this 3 by 10 if you take like this side and remaining if you take that side, let me write here. So then 3 by 10 means 0.3, that will be equals to 0.25 plus 3xn, then 3xn value is equals to 0.05. okay, so 0.05. so from this one if you calculate xn value equals to, so 0.0166 you will be getting. okay, so answer is 1. okay, like this, understanding. So may not be asking the same kind of fault. okay, if they ask LL fault or LLG fault and different, if the fault current value is same they have mentioned, if they have mentioned double, okay, so you have to mention, okay, so double this one like that. okay, so according to the problem you need to solve that one. okay, so buses for load flow studies are classified as, okay, so A, B, C buses they have mentioned. From the options we have to choose. So the load bus generally we will be calling as, okay, so PQ bus. okay, so the generator bus you will be calling as PV bus. Slack bus you will be calling as reference bus. okay, so this is what 3 other names also. From this one only we can get. okay, so this is the answer: PQ bus load bus, generator bus PV bus, slack bus. So this one is V and delta. okay, so remember one more thing. So what are the dependents, what are the independents, that also they may ask. okay, so at PQ bus, at load bus, what are the dependents and what are the independents? okay, so and at the generator bus, what are the known values and what are the unknown parameters, like that they may ask. okay, so based on this also you need to understand a little bit. okay, next question: the incremental fuel cost for 2 generating units given by IC1, incremental cost 1 equals to 25 plus 0.2 Pg1. So IC2 equals to 32 plus 0.2 Pg2. okay, where Pg1 and Pg2 are real power generated by the units. The economic allocation for a total load of 250 megawatt. okay, neglecting transmission loss is given, neglecting transmission loss is given by, okay, they were asking about Pg1 value and Pg2 value and incremental cost they have mentioned for two of the generators. okay, so and anyway total load they have mentioned as 250 means P1 plus P2 is equals to 250 megawatt. okay, so P1 plus P2. So if you have another relation like this, then we can solve. That's what, right? okay, anyway incremental cost for the economic generation, incremental cost must be equal. So that means 25 plus 0.2. so let's write P1. okay, and 32 plus 0.2 P2. okay, so this is the one, and if you simplify this one, so 0.2 also I will simplify like P1 minus P2 equals to 32 minus 25 is so 32 minus 25 is 7, and here 0.2 means 1 by 5. I will multiply, so you will get 35. okay, so if you don't know the calculation, you just do. okay, so P1 minus P2 we got like this, P1 plus P2 we got like this. If you add these two, okay, so if you add these two, then you will be getting 2P1 is equals to 250 plus 35, that means 285 you will be getting. So P1 value is nothing but 285 divided by 2 is 142.5. okay, so this much of megawatts it should be. okay, so P1. okay, so where is P1? So they have not given that option here. okay, so anyhow 142.5 it has to be, so they have given the wrong options here. So 142.5 it has to be. okay, so if P1 we know, P2 also we can know, so that will be 107.5 megawatt. okay, so that you will be getting. okay, so this is the two values, but they have given the wrong options here. So according to the options we need to choose. okay, so next one: the most appropriate operating speed in RPM of the generator used in thermal, nuclear and hydropower plants would respectively be. Okay, so they are asking about three power generating plants. In that, what is the speed of the generators they are asking. Okay, so anyhow we have high speed generators, those are called alternators or turbo alternators we may call. Okay, so no need to think about any missions point of view. So here we need some of the basic concepts of turbines. Okay, see, for thermal power plant, okay, so for thermal power plant and nuclear power plant, okay, so nuclear power station, so what kind of turbines we will be using means we will be using a steam turbine. Okay, so steam turbines. Okay, so steam turbines will be using. Okay, so high speed rotating the turbines these are, so there is no problem with the high speed. Okay, so and another one is so our hydroelectric. Okay, so hydroelectric. So here which kind of turbine we will be using means water turbine we will be using. Okay, so water turbines. Okay, so we will be using water turbines. Okay, so in the hydroelectric power station, so generally what kind of head will be there means high head, otherwise low head will be there. Water will be coming from the top. Okay, so it may not be coming as a free. Okay, it will be coming in the pipes only, but water will be coming, and this water should touch the blades, otherwise the buckets of the turbine. Okay, if these are the buckets, the water has to come and hit these buckets, and this turbine has to rotate. Okay, so the turbine shaft and generator shaft has to be connected like this with the coupling will be there between these two. Okay, so remember one thing, if this turbine can rotate at high speed, if this turbine is rotating at high speed, whatever water will be coming, so that water will be wasted more. Okay, like it will be continuously rotating, so the entire water may not be touching the buckets properly. Okay, so that's why instead of going for the high speed turbine here, if the speed of the turbine is less, like it will be rotating less speed, then all the water will be touching, and that force, that torque, it will be driving this entire generator. Okay, so that's a more comfortable thing. Okay, that's why the speed, okay, so the speed of the turbine, otherwise the rotational speed of the turbine, it has to be less here. Okay, so when rotational speed has to be less means definitely for the rotor also the rotational speed must be less only. Okay, understanding right? Rotational speed must be less. That's how we can confirm up to there. For the hydroelectric power station, the speed of the turbine, it must be less value. Okay, so no problem up to here. So then if you want increase in speed, then you will get more advantages right here. Okay, so magnetic losses will be less. And one more thing, so for the thermal and nuclear power plants, generally the speed of synchronous speed will be 120 F divided by P. We know F value equals to 50 hertz for our systems. Okay, so F value equal to 50 hertz, and number of poles, we are using turbo alternators here. Okay, so turbo alternators, so that means already high speed alternators, how many number of poles will be there? Generally P equals to 2. Okay, so very rare case we will be going for the 4 poles. Okay, so if anything required. Okay, so then it will be 120 into 50 divided by, so number of poles are 2 only. Okay, so how much you will be getting? 3000 RPM you will be getting. Okay, so this is okay, no problem. But if you want to use like this here, okay, so what will be happening? So again you have to go for if P equals to 2. If P equals to 2, okay, so then it will be like a very less number of poles will be there. This wants to rotate at higher speeds, right? So that means we need to use some gears here. Okay, some gears we have to use. If you use the gears, gear losses also will be adding. Okay, so why to go for all these things? Okay, instead of compromising with the number of pole, instead of compromising with so this speed here, so number of poles here, we'll go with so lower speeds. Okay, so that means the speed has to be decreased. Okay, for the rotor also the speed has to be decreased. Okay, so to decrease the speed, okay, so to decrease the speed, there is only one possibility. So the frequency we cannot change, right? 50 hertz is fixed. Okay, so to decrease the speed, number of poles has to increase. Okay, so number of poles has to increase. So that means Generally for the hydroelectric power station, so we can manage with a speed of 36 rpm to 600 rpm. These are the nominal values, okay, so minimum and maximum for the hydroelectric power station, okay. So for the hydroelectric power station, okay, so this is the rpm, general rpm we will be having. So comfortable value will be so around 300 rpm, okay. So most of the generators, okay, so you'll be having this 3000 rpm, okay. So wherever water turbines in hydroelectric power station, okay, so that's how you have to confirm. Anyhow, number of poles increase, right? Number of poles increase here, the weight of this rotating part will increase, weight of this rotating part will increase, so automatically, so with this one there will be more stability we will be getting, okay. So even the dynamics also, it will be having more proper rotational force will be having here, okay. So and some more explanations also there, okay. So in original classes we have discussed this, okay. So anyway, so here number of poles will be more and here number of poles will be only 2, okay. So answer for this question is 3000, 3000 and 300. This is the correct answer, okay. So there are more explanations also on this one, okay. So you understand this concept, and if you need anything also extend your conversations, okay. So next one, a large AC generator supplying power to an infinite bus has a sudden short circuit occurring at its terminals. Assuming the prime mover input and the load behind the transient reactance to remain constant immediately after the fault, acceleration of the generator rotor is, okay. So this is a lengthy, right? Question is lengthy only, so but we need to understand a simple thing, okay. So they have asked about, so it is a large generator, okay. So it is a large generator, so we need to understand whenever this is happening, whenever this is means whenever the fault is happening, okay. So it is connected to infinite bus bar, no problem. Sudden short circuit occurring at its terminals, okay, no problem. So after that, assuming the prime mover input and voltage behind the transient reactance to remain constant immediately after the fault, that means no subtransient reactance, no transient reactance, so no any steady state of reactance affecting this one, understanding, right? Nothing is affecting this. And at that time what they are asking, acceleration of the generator rotor, okay. So you know one thing, okay, so the accelerating power we can give it as, okay, so m into so d square delta by dt square, okay. So this is what they have mentioned, this is what equation, right? Okay, so we know accelerating power, so from the swing equation, okay. And what is this moment of inertia? So this moment of inertia is nothing but, so we can give it as, okay, so 2gh divided by the angular velocity omega, okay. So that means rotational velocity is, so m is moment of inertia, g is the rating of the machine, h is the inertia constant, okay. So if you substitute this one here, so then you will be getting pa equals to 2 into g into h divided by omega and d square delta by so dt square, okay. So this is what we have. What is this d square delta by dt square? This is nothing but our acceleration only, okay. So this is only the acceleration, this is the angle, okay, so our displacement. After that, so then d delta by dt we will be getting as the so velocity change, okay. So otherwise after that d square we will be getting as the acceleration. We know this one already. So this is the accelerating power, and they have mentioned assuming the prime mover input and voltage behind the transient reactance to remain constant immediately after the fault. That means that is not affecting, if reactance is not changing or it is a constant only, accelerating power also does not affect. So what you need to consider, how this d square delta by dt square is related to, C is related to, see the options, okay. So inversely proportional to the moment of inertia, okay. So next, inversely proportional to square of the voltage, so nothing related to voltage here, okay. So directly proportional to square of short circuit current, next directly proportional to the short circuit power, okay. So that's what they have mentioned. But you see, okay, so this d square delta by dt square is inversely proportional to this h if it go to other side, okay. So it is inversely proportional to so moment of inertia, otherwise inversely proportional to so the inertia constant, okay. So anything we can consider, okay. So anyway, answer is this one, no need of all this explanation also, okay. So directly from this one we need to get, okay, whenever whenever fault occurs, how the machine will be responding whenever fault occurs on the system. The rotor dynamics, how it is, if moment of inertia is high, then the swinging of that machine will be less. If moment of inertia is less, easily it will be swinging. Okay, so that means according to the load changes or according to the disturbances. Okay, if moment of inertia is less, then it will be so easily disturbing. If the moment of inertia is high, then it will be not easily disturbing. Okay, so from that one you can understand, so inversely proportional to the moment of inertia of the machine. Okay, so directly this question, this answer we have to give. Okay, so next question, if the short transmission line, in a short transmission line, resistance and inductance are found to be equal and regulation appears to be 0, so then the regulation is 0 only at the leading power factor loads. There are no other leading power factor examples. Okay, so anyhow, so regulation curve. Okay, so you will learn in the machine subject also, so no need to understand now. Okay, so next, steady state stability of your power systems is improved by. Okay, so one of the very good question it is, steady state stability improved by they are asking. Okay, so the first one, reducing fault clearing time. Okay, so one by one we will understand. If you reduce the fault clearing time, you are making it in the transient stability. Yes or no? So like some problem came and you are operating your, so this fault clearing time you are reducing, that means circuit breaker it is responding very fast and you have made some changes, so then it will be comes under the transient state, because whenever fault occurs at that time you are doing this one, so it comes under the transient state stability. Okay, so not a steady state stability. Okay, so next, okay, let's see this one. Okay, single pole switching. What is this single pole switching? For example, if a three-phase line is there, okay, so three-phase line is there, whenever fault occurs in one phase, all the three-phase pole, if three-phase circuit breaker, if it is open means all the lines will be opening. Okay, so that's also in the whenever fault occurs at that time. Okay, so what they are suggesting, why to open all the three poles, open only one pole. Okay, that means single pole switching. Okay, that means only one pole has to, wherever fault is there, that pole only has to be open. Like that they have mentioning suggestion, but this is also related to transient state stability. Okay, not in steady state it is. Okay, so to make the reliability of the system we are using this in transient stability. Okay, so next, decreasing generator inertia. Again, generator inertia, when it comes, whenever generator is working properly, okay, even though inertia is less or more, no problem. If it is working properly, so there are no load changes, so nothing is there, then everything works properly. Okay, if any load changes are there, then immediately which will be having, if the inertia is less, then more swinging of the machine will be there. Okay, so that's how inertia of the machine affects the generator swinging definitely, and it comes under again whenever fault occurs, at that time only it will be so occurring. That means this also transient state stability. Okay, so next, using double circuit line instead of single circuit line. Okay, so what is this option? See, between two stations, instead of using the single circuit line, okay, so single line, we can make it as a double circuit line. So that means whenever you make it as a double circuit line, the entire reactance will decrease. Whenever reactance will decrease, another problem we have seen, P max. Okay, so P max will increase. Whenever P max increases, so that means it is improving the steady state stability limit. Okay, steady state stability increased. Okay, steady state stability of the power system is improved by using double circuit line instead of single circuit line. Okay, so there are certain methods for the steady state stability limit improvement, and similarly transient state stability limit improvement. Okay, you need to study this, then if you understand what is steady state stability and what is transient state stability in power systems, then only you can be understanding more concepts for the entire power system network. Okay, even though when you work also, how these rotor dynamics are there, if you want to understand those things, definitely you need to understand about this rotor angular stability. Okay, so anyhow answer for this question is the second one. Okay, And the next question is, during a disturbance on a synchronous machine, the rotor swings from A to B before finally setting down to steady state at point C on the power angle curve. The speed of the machine during oscillation is synchronous at points. Okay, so they are asking about rotor angular stability concept only again. Okay, see, the first concept we will be learning in that unit is, so whenever some disturbance happens on a synchronous generator or rotor or motor, okay, so let's take the generator. Okay, so what I have did is, so on a power angle curve we are taking this entire characteristics. Okay, so this is the electrical power output and this is the input, this is the delta. Okay, so angular the rotor angle or so delta angle we will be considering. Okay, load angle it is. Okay, so anyhow this is the power angle curve. Okay, so you know already, so P electrical equals to P max sin delta. Okay, so delta is this one and P is this one. So what is this? This is the P max. Okay, so now previously the generator is working at this one. Okay, so like this is the input, okay, for the steam input for the generator it is. Okay, so our water input it will be, understanding, any input only it is. Okay, so now what we have did, we have increased the input from here to here. This is PS2, understanding, so this is PS2 now. Okay, so that means whenever you increase, definitely delta wants to change or not, from here to here it wants to change. Okay, that means the rotor will be swinging from this angle too, so it will be increasing like this. Definitely it will not stop here because there will be some inertia, with that it will be increasing. Previously here at this point, okay, so it will be working at a certain synchronous speed, mostly it will be 1500 rpm at that time. Okay, so now whenever you increase, it will be going to some place, at some place it will be reaching again synchronous speed and it will come back. Okay, so here also it will reach the synchronous speed, and they are mentioning this is point A and this is point B. Okay, let's take this one, these points again. This is B and this is A. Between, from here to here it has swing. Whenever you increase certain input, here it will not stop, it will go and again it will be coming back again. It will continuously swing like this. Later at some position, okay, so here it will be, so this point is called C. Okay, at some point it will be settling down, C. So this is what they have mentioned already. Okay, so if you know this concept before, directly from this you can understand. Okay, so anyway these are the 3 points, and they are asking at what places you will be having the speed of the machine. Okay, so speed of the machine, synchronous speed. Okay, so that's what they are asking, right? Okay, so the speed of the machine during oscillation is synchronous at points. At which points? Previously it is synchronous speed here. After reaching here also we will be having synchronous speed, and here while reaching like this in this direction when the rotor is traveling, then it will be omega s is more than synchronous speed. When it is coming in this direction, rotor again, that means swinging in this direction, omega s is less than synchronous speed. Okay, so that's what happens. Okay, so at C point, so sometimes it will, when it's swinging in this direction, more than synchronous speed. When it is swinging like this, less than synchronous speed. But at A and B you will be having the synchronous speed. Okay, so then slowly like this. Okay, so continuously it will be swinging. A point will become as A dash, A double dash, A triple dash, like this. It will, the swing, okay, so the swing area will be decreased and finally it will be settling down here. Okay, so like that it will happen. Okay, so anyhow during the swinging, okay, omega s synchronous speed is here and synchronous speed is here. Both A and B points will be having the synchronous speeds. Okay, at C greater than omega s and less than omega s also possible. Okay, so this is the question, one of the important question. Okay, next one, if the fault current is 2000 amperes, the relay setting is 50% and the CT ratio is 400:5, the plug setting multiplier will be. Okay, so they are asking about plug setting multiplier. Okay, so what is this plug setting multiplier? So for the relay we need to set this plug setting multiplier, according to that it will be operating. Okay, so we know this one. So what is this plug setting multiplier means? So the fault current referred to secondary. Okay, so fault current referred to secondary. So divided by, okay, so divided by current setting value. Okay, so current setting. Okay, so this is the one we have to use formula. Okay, so what is this current setting? So current setting they have not mentioned, but they have given a relay setting. Okay, so relay setting is 50%. Okay, so relay will be in the secondary side of current transformer. Secondary side of current transformer, current whatever is there, 50% of that value is called current setting. Understanding? So current setting value is 50% of 5 means the current setting is 2.5 amperes. Okay, so 2.5 amperes only. Okay, now secondary side of fault current, primary side or original fault current is 2000 amperes. Current transformer rating is 400:5. Based on this one, okay, so based on this one, so the 2000 amperes to other side current transformer, if you transfer, what will be happening? The current value IF secondary you will be getting as, so 2000 means you have to use the 5 times. Okay, so that means 25 amperes you will be getting on the secondary side. Okay, so that is the fault current referred to the secondary side. Okay, so this is the 25 ampere. Let's substitute here 25 amperes divided by 2.5 amperes, so that will be equals to 10 amperes. Okay, so this is the answer. Okay, so like this we have to remember. Okay, so this concept. So plug setting multiplier. Okay, so this formula you remember. Okay, so generally IF in secondary divided by, so all these CT ratio, all these formulas will be there. Generally you will confuse, but remember only this formula, and derive for this one values, then you can substitute directly. Okay, so this is the answer. Next one, reactance relay is normally preferred for protection against, okay, reactance relay. So for the earth faults only we'll be using. For the phase faults means internal faults, those are, okay, so we'll be using the methods. Okay, so not directly one relay we will be using, MEDS price protection we will be using. Okay, and open circuit faults. Okay, so open circuit faults are called, so it is not continuous faults, otherwise we don't know when these faults will be happening also. And what we can do is we have to avoid this maintenance, continuous maintenance is required to avoid entire open circuit faults. Okay, otherwise during the during the rainy season only this open circuit faults will be happening. So for that some different solutions we have. Okay, so not like relays cannot do anything, because whenever open circuit occurs there will not be any current, and even for the operation also. Okay, so that's why earth faults, for the earth faults reactance relay will be using, and there are reasons for the earth faults why we are using the reactance relay. So whenever fault occurs towards the ground, okay, that means LG fault or LLG fault or triple LG fault, so then the reactance continuously varies. Okay, so the reactance continuously varies, that means zero sequence reactance will be continuously varying. So based on that, so we can operate this relays. If you keep this relays, we can understand the fault very fast. Okay, so that's how reactance relays we will be using. Okay, so next one, which of the following statement is true? Okay, steady state stability limit is greater than transient state stability. Okay, so this is simple question only, so we need to understand what is steady state stability and transient state stability. For example, one generator has installed capacity of, okay, so let's take the recent generator anything. Okay, so like 800 megawatt, this is the generator capacity. Okay, so this is the capacity, understanding? So this is the capacity. Now it is generating like 300 megawatt. Okay, so now it is giving 300 megawatt. Okay, so this is the maximum, for example. Okay, so then it will be called this much of gap is there. Okay, so there is no problem, you can increase how much more. It is 300 now, total 800 means 500 megawatt gap is there between. That means this much of reserve is there at present. Okay, so this much of reserve is there, you can increase to this much. But you see, if you increase suddenly this much 500 megawatt, it will not be stopping here. So it will be increasing more and decreasing. The generator will easily loses the synchronism. Okay, so that means we should not increase this much. Understanding, right? There should be some limit, right? So it may be generating up to 750 megawatt, because there may be some swings, some sudden faults may come. That's why you should have certain capacity. This is also very narrow capacity. It should have more gap between this limit and this maximum value. Maximum means capacity, installed capacity. Understanding? So this is called up to this much level, the generator will be so safe and it will be working properly. That is called steady state. Okay, so steady state limit. Understanding? So up to this much, that means this generator we can operate up to this 750 megawatt, then it will be stable. After this, if you operate, it may enter into the unstable region and it will lose the synchronism. That's what it means. Okay, so now see, up to 750 you can increase, right? Now it is operating at 300 megawatt, means how much you can increase? Like 450. Can you increase 450 at a time? You cannot increase. If you increase the 450 also, it wants to give it again, like it will be swinging to the other side and it has to come back. It may not come back. It may not reach the synchronism again. So that's why what you have to do, you should not increase suddenly this much. A step by step increment, like so 300 to 50 more I will add, like 50 megawatt more I will add. That means now it will become 350. It will swing and settle. Next again 50. Okay, it will swing and settle. Again 50. It will swing and settle. Again 50. It will swing and settle. Like what we are doing, every time we are doing this 50 only. If more than 50 if you add, it will swing more. If 150 if you add, it will swing even more. If 200, it will swing more. That means it has certain swinging limit. It has to be in the synchronism, means we need to give it only a limited value. So that is called transient state stability limit. Okay, so that means a step by step increment, a slow value we have to increase. That is called transient state stability limit. Okay, what is steady state stability? You see, so this much is the steady state stability for the generator now, and transient state stability is lesser value. Okay, so steady state stability is the maximum. Okay, so but is there any possibility like transient state stability is equals to steady state stability? Means it's not possible, because at a time if you increase the 450 also, so what will happen, it will directly reach the, so out of this swinging. Okay, so that's why, so what we have to do, the transient state stability, it should be always very less value and it has to be less than this steady state stability limit. Okay, so that's what answer for us, and no need to have this all analysis. Okay, if you are understanding for the first time, then you need this analysis, otherwise no need. Okay, so like steady state stability limit is greater than transient stability limit. Okay, next one, to prevent maloperation of differentially connected relay while energizing a transformer, the relay restraining coil, okay, so is based with, it's not based, okay, it's a biased. Okay, so to prevent maloperation of, okay, so relay, what we have to do, we need to do the so harmonic analysis of that one. After that we will understand there are certain higher harmonic in transformer whenever it's starting. So that is second harmonic current. So then it has to be biased with second harmonic current. Okay, so anyway, so that is required. Okay, so in when you are studying about three-phase transformers, you will understand about this how we need to so check this second harmonic current and how it is helping and how it is giving the so transforming action also. Okay, so anyway there you will understand. Answer for this is second harmonic current. Okay, next one is a lightning arrestor connected between the line and earth in a power system. So why they are connecting lightning arrestors? That's what they are asking. So see the options. Protects the terminal equipment against traveling surges. Okay, protects the transmission line against direct lightning strokes. Next one, suppresses high frequency oscillations in the line, reflects back the traveling wave approaching it. Okay, so what is the answer? Lightning arrestor they are asking. Lightning arrestor. Okay, so lightning arrestor why we are giving means to suppress to suppress the voltages. Okay, so to suppress the voltages. Okay, so that which voltages, higher voltages if anything is there, so that they are suppressing. Okay, so that means to protect, definitely it has to protect the terminal equipment against traveling surges. Okay, what are these traveling surges? Let's see. Okay, so next one, protects the transmission line against direct lightning strokes. So whenever if you see the transmission pole or any tower like this, so there will be first one, second one and third one. So here our actual conductors will be going like this. On the top there will be one thin conductor. Understanding? So on the top there will be one thin conductor, that is not power conductor. Okay, so this is called a guard wire, otherwise a ground wire. Okay, so ground wire, otherwise shield wire. Okay, so shield wire will be calling. Why it is given means, whenever any direct stroke attack on this one, like lightning, any lightning will come, then that has to go through the ground, through these towers, not only one tower, any tower. Okay, so but that is not connected to our power lines, because there is certain insulator. Okay, whenever we have like this one side, so there are certain insulators like this insulators will be there. After that only, so like this is suspension type. Okay, so after that only conductor will be present, so the current will be going like this only. Okay, so it will not enter into the power lines. That is what the idea. Okay, so that's why we have given this one. Okay, so anyway, in different question we will understand more concepts about this one, more points about this guard wire, otherwise shield wire. Okay, so that is the one we have given for the direct lightning strokes on the transmission system. Okay, next, protects the terminal equipment against traveling surges. What is this traveling surges means? Whenever some switch is on, otherwise whenever some switch is off, there may be some sparks coming. Yes or no? Spark will come, right? Even in our home also we can observe this. But when you are operating 400 kilovolts, 400 kV line, okay, so when you are turning on and turning off, at that time very huge spark, otherwise very huge, okay, so traveling surges will be coming. Okay, so that voltage will be traveled for some of the line. Okay, so then what happens, those all has to be suppressed. So that's why to protect against this one, we have to give this lightning arresters. Some sparks will be producing at that time, so that sparks has to be so suppressed using this lightning arresters. Okay, so next, supplies high frequency oscillations in the line. Okay, so no suppresses high frequency oscillations. High frequency oscillations will not be decreased using this one. Okay, so reflects back the traveling wave approaching it. Okay, this is also not the correct reason. Okay, so next question, equal area criterion. Okay, so what it will be giving, so if you have understood the classes generally, so you can directly give this. Okay, so I have already given here previously A1 equals to A2, so that is exactly so giving the solution for us. So it is absolute stability. Okay, equal area criteria will give the absolute stability. Okay, so next one, so this is also one of the battery question. Okay, so directly, so I have already marked this one. The storage battery generally used in electric power stations is lead acid battery. Okay, so why this will be there? Okay, this is a power station only, right? You don't have the power like that, so it needed sometimes. Okay, so sometimes you need to charge and sometimes you need to discharge. So this so batteries are definitely required in the substation. Okay, so in the batteries concept you will understand this again. Okay, so next one, in a synchronous generator delivering a lagging power factor load, options, the excitation EMF leads terminal voltage by power angle. Okay, so they are asking about some relation. Okay, so between the power and angle. Okay, so and voltage also they are asking EMF. Okay, so anyway, so this synchronous generator delivering a lagging power factor load. Okay, so let's draw the single line diagram. So here you will be giving E at, okay, so this is, so V at an angle of 0, E at an angle of delta it is. If it is reactance X, then the power we will be giving it as, okay, so EV by X into sin delta. We know this one, okay, for the short transmission line. Otherwise, directly the excitation EMF leads terminal voltage by power angle, okay. Only this equation they have given. If you know this equation, otherwise if you know this single line diagram, you can answer this question directly. Okay, which of the following, okay, so this is a networks question only, okay. In the last video I forgot to add this question, that's why I have kept it here. So which of the following theorems enables a number of voltage source to be combined directly into a single voltage or current source, okay. So some of the theorems they have mentioned, following theorem enables number of voltage sources we can combine, okay. So what is a voltage source? Generally voltage source means any voltage in series with resistance, that's called voltage source, okay. So like that, many voltage sources in series with their internal resistances connected in parallel, so we can make it as a single voltage source in series with resistance, okay. So like this we can represent. What is this theorem? This is called Thevenin's theorem only. Yes or no? Any big network which some, so at least one source and resistances can be transformed as a single voltage source in series with resistance, so between the terminals A and B, okay. So same terminals A and B, okay. So this is called Thevenin's theorem. Yes or no? Option is not present, okay. So this is the one, but what is the option? Compensation theorem, reciprocity theorem, superposition theorem and Millman's theorem, okay. So what is this called? Means this is nothing but a power plant. Understanding? This is nothing but a power plant. So there will not be only one unit in power generating station. So many so many generators they will be connecting like this. So and this is also called as parallel generator system, okay. So parallel generator system. Understanding? So there will be so many, like recent any power plant you take, at least 2 or 3 units will be there, 4 units will be there, 5 units also will be there, okay. So this is a parallel generator system, and whenever we have like this, directly we can represent like this, there is no problem, okay. So there is another name also for this one, this is called Millman's theorem, okay. So anyway, in classes we will be understanding, so directly we can understand this concept, okay. So Millman's theorem it is, so either current sources or voltage sources, anything we can consider. It is also called as parallel generator theorem, okay, and it is just the extension of Thevenin's theorem only, okay. So or you can consider as Norton theorem also. If this voltage source in series with resistance transform as a current source in parallel with same resistance, okay, so then that is Norton theorem, okay. So anything is same only, like Thevenin's, Norton's and Millman's theorem, these are all same only, okay. If you are our student, then you will understand, okay, how I will be teaching this concept in our classes. So I will teach with this example only, Thevenin's, Norton's, Thevenin's, Norton's and nodal analysis, all these, okay. So we will be understanding from only one circuit, okay. So when we are studying about the theorems, okay. So anyhow, so answer for this question is Millman's theorem, okay. So in our next video we will understand about power plant engineering questions, okay. So anyway, all the best, thank you so much.